Have you ever really stopped to think about the rules of math? I'm not talking about the complicated stuff, but the absolute rock bottom basics. It turns out all those simple ideas we learn as kids, numbers, counting, adding, they're all built on this surprisingly elegant and really strict foundation. So today, we're going to peel back the curtain on these fundamentals, numbers, sets, and the operations that make them all work.
It sounds almost silly to ask, right? What is a number? I mean, we use them all the time, for counting, for measuring, for basically everything. But if you had to define one without actually using the word number, could you do it? It's a lot trickier than it seems, and the answer is really the first big step on our journey today. So here's our roadmap. We're going to start with the very idea of a number. Then we'll get into the first numbers we ever learn, the counting numbers, and that absolute game changer, the concept of zero. Once we have our numbers, we've got to learn how to organize them into these things called sets. And then comes the fun part, putting them into action with operations. Finally, we'll uncover the hidden rules that everything else in math has to follow. So let's get right into it. What is a number? Well, it's not the squiggly line you see on a page. The reality is, it's a lot more abstract than that. This slide right here, this gets to the absolute heart of it. A number is purely an idea. That feeling of threeness, whether it's 3 apples or 3 cars, that is the number. The symbol 3 is just a label. It's a piece of writing we've all agreed represents that idea. But the symbol itself isn't the number, any more than the letters WATER are actually wet. Okay, so if numbers are ideas, what were the very first number ideas that humans came up with? Well, they're the ones we all learn as kids, the very first time we start to count things. These are the counting numbers, or as they're also called, the natural numbers. They start at 1, and they just keep going, forever. What's so amazing about them is their simple, perfect structure. Every single number has a successor, a next number that's just one larger. 2 follows 1, 3 follows 2, on and on in this infinite, unbreakable chain. Now for a really revolutionary idea, what if we take our counting numbers and we add just one new concept, the idea of nothing, the number 0? With that single addition, we create a whole new group, the whole numbers. You don't really start counting from 0, but adding it to our toolbox makes our entire number system incredibly more powerful. So we have our numbers. But if we want to do any serious math, we can't just have them floating around all over the place. We need a way to organize them, to talk about specific collections of numbers. We basically need containers. And in math, that container is called a set. A set is simply a collection of distinct things. Seriously, think of it like a bag. You can have a bag of marbles, a bag of whole numbers, a bag of whatever. The items you put inside, those are called the elements of the set. Now, if a set is our big bag of numbers, a subset is what you get when you reach into that bag and pull out a smaller bag. The only rule, and it's a big one, is that every single number in your new, smaller bag must have also been in the big one to begin with. It's literally a set within a set. Let's make this a little more concrete with a few examples. Imagine our main set, our big bag, is all the whole numbers. From that bag, we could create a subset of just the odd numbers, or the subset of just the even numbers. We could even make a tiny subset, like the whole numbers from 0 to 9. Each one is a unique collection, but every single element inside them is still, at the end of the day, a whole number. Okay, so we figured out what numbers are, and we've organized them into sets. The next logical question has to be, what can we actually do with them? This is where the action happens. And that action is called an operation. An operation is just a rule for taking numbers and combining them to get a result. Think of them as the verbs of math. If numbers are the nouns, then operations are what let us actually do things, like add, subtract, multiply, and divide them. And here are the most famous ones, the ones we all know. We've got our symbols, which are just shorthands for the procedures, and importantly, we have specific names for the results. The result of an addition is called a sum. The result of a subtraction is a difference, and so on. This vocabulary is really key to speaking the language of math clearly. This brings us to the most crucial part of our whole journey. See, in math, you can't just make up an operation and call it a day. For the system to be stable and reliable, any operation has to follow some very strict rules. It has to kind of earn its place. Let's look at what makes an operation official.
And this right here is the main rule. It's called a binary operation. Now, this definition sounds super complicated, but it really just breaks down into two simple promises. Promise 1, for any two numbers you pick, you will always get one and only one answer. That answer is unique. Promise 2, the answer you get will also be a member of the exact same set you started with.
Addition on the set of whole numbers is the perfect example. Let's test it. Pick any two whole numbers, say 8 and 7. The operation of addition gives you one single unique answer, 15. And is 15 a whole number? Yep, it is. It keeps both promises. The answer is unique, and it stays within the original set. It passes the test.
So this is the test that every binary operation has to pass. You pick two elements from your set, you apply the operation, and the unique answer you get must be an element of that very same set. The process has to be a closed loop. You can't get kicked out of your starting group.
Now, addition seems to play by the rules perfectly. It's really well behaved. But what about the other basic operations we know and love? Does something as simple as subtraction follow this same strict rule?
And here is the big reveal. Let's test subtraction on our set of whole numbers. We start with two whole numbers, 7 and 8. We apply the subtraction operation. But the answer we get is -1. And is -1 in the set of whole numbers? Nope, it's not. The operation has kicked us right out of our original set. It broke the second promise. This leads to a pretty surprising but totally formal conclusion. Our source material puts it perfectly, so I'm going to read the quote. Because there are pairs of whole numbers whose difference is not a whole number, subtraction is not a binary operation for whole numbers. Simply put, it fails the test. Now, this doesn't mean subtraction is broken or useless, but it does mean that for the set of whole numbers, it doesn't play by the official rules. And that's really our big takeaway for today. Math isn't just about getting the right answer. It's about this hidden world of structures and sets and rules that have to be followed. We just discovered that something we've all been doing since we were kids actually fails to meet a really formal property. So the question that leaves us with is this. If even simple subtraction has this hidden complexity, what other rules are lurking just beneath the surface of the math we think we know so well?